Hi everyone. Okay, so in this video we are going to continue with dynamic programming in reinforcement learning, and we are going to start with our first algorithm, policy iteration. Policy iteration. Okay, so the way this algorithm works is it starts with a random policy, and a next step after this policy, what is done is policy evaluation. Policy evaluation, and it works by getting a value function, by computing a value function, and essentially here we are computing how good this policy is. Okay, and then after this policy evaluation, there is a policy improvement, essentially getting a better policy improvement. So in this particular step, we update the current policy that we have by acting greedily with respect to the current value function. So we kind of get a new pi, which is essentially greedy with respect to the v that we currently have. So this is the way it works, this policy iteration. You get you have a pi, you get a bet, you do policy evaluation, then policy improvement, then again policy evaluation, policy improvement, till there is convergence. But technically, what happens in this policy evaluation is this. This is the system. This is what happens. So this is the first term here is the value of state S under the current policy pi L. So this works in iterations. So in each iteration, you repeat this process for all the states that you have. And each iteration has its own pi. So that is why we have pi L here. So this is V, value of the current state under pi L. This is the immediate reward. This is pi L, and this gives us an action to have a state action pair. So this is the immediate reward for which is dictated, of course, by pi L. Okay, we already know this. This is gamma. This is the discount factor, which tells us how much we care about future rewards compared to the immediate ones. This is our expectation. Now, from state S, you can transit to S prime. So this is the probability of that S prime, and this is the value of that S prime. We also have a pi here. So this is the expectation. Don't forget, when computing the expectation, you need to consider when, for example, the policy is deterministic or when it is stochastic. I already have a video on different combination of types of environments: stochastic environment, deterministic environment, stochastic policy, when computing, considering all that when computing this expectation. So this is essentially the value, this probability of the next state times the value of the next state. Of course, this is under policy pi L. Okay. Now, you do this for all the states that you have. In this policy improvement, what happens? Oh, sorry. This is technically what happens. So this is the updated, more like the updated policy at state S. So this is like the new policy. I think of it like in the next iteration you are not getting pi L, but pi L plus 1, like the updated version. This argmax is essentially, here we are essentially selecting the action A that maximizes the expression inside this bracket, which is the immediate reward plus the expected future reward. These expressions are similar. I don't have to go into explaining them, but I'm going to give you a numerical example to make it clear. We are going to be using this system. I have been using this for quite a while. I would like to change it, but I'm using this for consistency and to make the example simple. Okay, so let's start with example for this policy iteration. Now, of course, this is our system that we are using. Let's define the environment. Well, the agent possible actions are left, okay, it's like a set, left, right, up, and down. So this is the action set, and the reward, I'm going to use minus 0.1. For all the different rewards, immediate rewards, I'm just using this for simplicity. The environment is deterministic, meaning that taking an action always leads to the same next state. So there's no randomness. Now, let's start with this policy evaluation for states. Let's pick state 5. So policy evaluation, state 5. This is 5. Okay. Now let's assume that the initial policy, the initial random policy, assigns up. So pi of 5 is up, assigns up to state 5, and the the value of each state start at 0. Typically, initially, of course, the policy can be this, and the value for all the states is 0. Typically, both this and this, I mean, that's what you do in programming. But the more you do this iteratively, the values actually converge, because we already know the full dynamics of the system. We have the full knowledge. We have the reward system. We have the probability matrix. We know everything. So at the end of the day, we are going to get the optimal value function. So they converge, but initially you start with random values. Now, for state 5, the policy tells it to go up, which leads it to state 1. So let's compute the value of state 5. The value of state 5, based on this formula, it is the immediate reward. Immediate reward is minus 0.1, this, plus gamma 0.9. Let's say gamma is 0.9. Okay, gamma 0.9. And then the value of the next state. So this is a deterministic environment. So this term is essentially 1. And the policy that I'm using is a deterministic policy for simplicity. So this term erases. So we'll be left with just the value of the next state. And the next state is state 1. And let's say the value of state 1 is 0.0. So value of state 5 will be minus 0.1. Minus 0.1. Typically, initially it is this, but the more you run the algorithm, it's going to change and converge. Okay, and then we have done this for state 5. We have to, based on the algorithm, do it for all the states that we have. And then next we do policy improvement for state 5. We are just working for state 5 for this particular numerical example. So in state 5, we need to evaluate all possible actions at state 5. In state 5, the agent can go left, right, up, down. So we need to compute the values of that. For up, when the agent decides to go up, it will go to state 1. So let's compute the value. It's going to be minus 0.1 immediate reward plus gamma 0.9 times the value of state 1, 0.0, which is minus 0.1. From state 5, it can also go right to state 6. And okay, imagine the agent is currently in state 5. So here in the diagram, it is like it is in state 6. No, it is actually in state 5. Sorry for that. Anyway, for right, it is minus 0.1 plus 0.9 times the value of, when, for example, here it can go right to state 6, and the value of state 6 is 0.62. And that will be, I mean, when you, sorry, let's sorry, I mixed it up. Let's say the value of state 6 is 0.8. And you do this, you're going to get 0.62. Okay. And now for left, it can get to, from go to state 4. Let's compute the value. It's going to be immediate reward plus gamma times the value of state 4. You do that, let's say you get 0.35. It can also go down from here. Let's compute the value. It's going to be immediate reward plus gamma times the value of state 9. You do that, let's say you get 0.25, so 0.26. It's the same thing, but for my example, it is 0.226. Now, the maximum value here is comes from going right. Okay, 0.62, which is the maximum value. This is what the policy improvement algorithm tells us. So you do this, we have done this for state 5. You repeat this for all the states that you have. Now let's do policy evaluation again. Oh, sorry. Policy evaluation, state 5. Now we have to, now before the policy of state 5 was up, now it is going to be actually right. We are going to update it to right because here the maximum value is 0.62, which came from going right. So pi of state 5 is going to be right. The policy of state 5 has changed. Now let's compute the new value of state 5. It's going to be immediate reward minus 0.1 plus gamma 0.9 times, hope you can see this, all right, 0.9 times the value of state 6, 0.8, and you are going to get 0.62. Now, the value of state 5 is now 0.62. It has changed from previously, what was it, minus 0.1 to this new 0.62, which indicates that the new policy has improved the expected return at state 5. So as you repeat this process, the values will stabilize and stop changing, which will indicate that the policy has converged. So, and then after this for state 5, you do this for all the different states. So this is policy, this is the policy iteration algorithm. You evaluate, improve, then repeat until convergence. Okay, so this is it. Thank you for watching. Let me know if you have any question in the comments. Bye bye.